Okay, I think we'll get started. So we've been talking about chemical reactions in a general sense through the development, or early development here of thermodynamics and the chemical potential. We will come back to that in a bit, but in the meantime, it's important to look at some specifics about chemical reactions and then learn how to do some calculations surrounding chemical reactions. So today we're going to talk about chemical reactions and stoichiometry. So a chemical reaction, as we've been talking about, is reactants goes to products. There can form an equilibrium here eventually, there always does, or we can be out of equilibrium. Either way, we write the same chemical reaction formula, or chemical equation as it's sometimes called. Let's take an example here. Let's look at C6H6, which happens to be a compound called benzene, a very important compound industrially, in nature, in synthetic chemistry. And we're going to react it with oxygen. This type of reaction is called a combustion reaction, very important classification of reactions, where we're combusting or burning a hydrocarbon, hydrogen and carbon, in oxygen. So here's an example of a very important reaction. And combustion reactions create carbon dioxide and water. Now, we could say, okay, this, as written here, it just says benzene is reacted with oxygen to form carbon dioxide and water. It doesn't give us the quantitative relationship between the benzene, the oxygen, carbon dioxide, water, and that has to happen at the moles level. So a chemical reaction is talking about moles most directly. So what we need to do is then balance the chemical reaction, and this can be sometimes just trial and error. There are a few systematic things that you can do to help yourself out. Let's balance this. What we want to do is notice that the oxygen is all by itself. If there's anything all by itself, leave that for the end, because you can freely adjust that without changing the other numbers. Notice if we were to adjust the amount of benzene here, we would change both the carbon and the hydrogen. Now, they're certainly not all individuals, so some of that's going to happen. So we can choose one, and we can say, okay, I've got 6 carbon over here, I've got 1 carbon over here. So if I multiply my carbon dioxide by 6, then I will have the requisite number of carbons. I have 6 and 6. Now, we can look at the hydrogen. Remember, we're saving oxygen for last. Hydrogen has 6. We have 2 here in water. So if we multiply now, sorry, I guess we're on this line now. If we multiply by 3, then we end up with the right number of hydrogens. 6 hydrogens, 6 carbons. We're all good there. Let's count the number of oxygens here. So there's 6 times 2, which is 12, plus 3, which is 15. So we go over to this side, we have only 2. So we need to multiply by 15 halves here. Now, 15 halves is a perfectly good number, or 7.5 is a perfectly good number for what are called the stoichiometric factors. Oftentimes you will see the equation multiplied by multiplied up until all of the stoichiometric factors are integers. There's no right or wrong way to do that. You can always multiply by any value, so any n, you can multiply this whole equation by, and you still have a balanced reaction. All right, well, let's figure out how to interpret the stoichiometric factors. And there's 3 different things we'll talk about here. Most directly, this is basically a sentence saying 1 mole of carbon dioxide, 1 mole of benzene reacts with 7.5 moles of oxygen to form 6 moles of carbon dioxide and 3 moles of water. That's the most direct thing that this balanced chemical reaction is saying. So it's most directly on the moles level. Now, we can talk about the molecular level, but we have to be a little bit careful. Notice, for one, we would not say 1 molecule of benzene reacts with 7.5 molecules of oxygen, because we can't have half number of oxygens. So here we would want to make sure our stoichiometric factor, our equation is multiplied up so our stoichiometric factors are all integers. Then we can say overall two molecules of benzene react with 15 molecules of oxygen to form 12 molecules of carbon dioxide and 6 molecules of water. Although even there we need to be a little bit careful. This is true of the overall thing that happened. Yes, 2 moles of benzene have gone away and 15 moles of oxygen have gone away and 12 moles of carbon dioxide have been produced, or molecules, and 6 molecules of water have been produced. So yes, that has happened. But as we will see when we talk about chemical kinetics, it does not at all mean that 15 molecules of oxygen collided with 2 moles of benzene to create this product. There are multiple steps involving different amounts of molecules each time. So you can read it as at the molecular level, but you have to realize that it is an overall statement about this many molecules went in, this many molecules came out. And then finally, for mathematical convenience, you can view the chemical reaction simply as a conversion factor. It says, for this reaction, 1 mole of benzene equals 7.5 moles of oxygen and 6 moles of carbon dioxide and 3 moles of water. So we can say that's a conversion factor for this reaction. For this reaction. So if we have a different reaction, of course, we have a different conversion factor. So they aren't conversion factors in the sense that there's 12 inches in a foot, for example. There's always 12 inches in a foot. Here, 7.5 moles of oxygen equals 1 mole of benzene for this combustion reaction. All right, so now we can go ahead and use this in a calculation. And in fact, we'll use the conversion factor idea the most. And we will, this might be the first time that we've really used this process called unit analysis, or this bookkeeping called unit analysis. It can be applied to the more physicsy type problems that we've been working on, but it isn't quite as effective there. But it's very effective in chemistry type problems involving grams to moles, moles to grams, and stoichiometry. So the basic idea here is we might want to know, okay, if I have this many moles of benzene, 0.3 moles of benzene, how many moles of oxygen are consumed along with that? And so that's a direct calculation using the conversion factor. So we write out 3 moles of benzene, then we write the stoichiometry as a conversion factor, and then notice the units here. This is what's so nice about this technique, is that you almost can't be wrong as long as you put the numbers in right and use your calculator correctly. The units will tell you if you've got these set up right. And so we are left with moles of oxygen, which is what we were perhaps interested in. So this is utilizing the chemical reaction in a step of the calculation. Let's do a little bit more elaborate calculation. Let's say we have 35 grams of benzene and we want to know how much water, how many grams of water is produced. Now, again, the reaction is always moles, not grams. So we have to do our conversion of grams to moles and moles to grams. Now, that was done way back quite some time ago in Introduction to Physical Chemistry 1. So if you do need to go back and review that, you should do that. That's grams to moles, moles to grams is just something that you have to be able to do very, very readily. All right, so I've looked up the molecular weights of water and benzene. And so here we have it. So we just kind of go again through a series of conversions. So we have 35 grams of benzene. Well, there's 78 grams of benzene in every mole. Then there's 1 mole of benzene for 3 moles of water. So there's our chemical reaction as a conversion factor. And then there's 1 mole of water is 18 grams of water. And again, you almost can't go wrong. Multiply that through, and at least we know the units are right. Now, I might have put that into the calculator wrong, and so it's always good to kind of double check that. But this unit analysis, as it's called, this boxing of these really helps prevent errors or helps catch errors. Let's just do one more example. Let's say we produce 100 grams of water. How many grams of oxygen were consumed? Well, again, 100 grams of water, we can convert that to moles. That's in this step. Then it's 7.5 moles of oxygen to 3 moles of water. In that step, there's where the chemical reaction sits, right there, the stoichiometry of the reaction, and then the conversion back to grams, and we get 440 grams of oxygen. All right, so here's using the chemical reaction to complete calculations of this type. We're going to talk a little bit more about this for the next couple of lectures, and then we'll get back to more of the general approach to chemical reactions.